In this video, we're going to look at the trends in specific groups of the periodic table. We're going to be looking at the chemical properties or how the elements in a specific group will react. This is largely determined by the number of electrons in the outer energy level. We saw this in bonding. If we took group 7, for example, it requires 1 electron to fill that outer shell. All of the elements in group 7 react in the same way or bond in the same way. Group 1 elements will bond in a similar way, meaning they have some similar chemical properties to each other as well. We could apply this to all of the groups across the periodic table. First of all, let's look at group 1, the alkali metals. These are very reactive due to their low ionization energy values. So it's very easy, it requires very little energy to remove their most loosely bound electron. For that reason, they don't even occur free in nature. You won't find just sodium on its own. You'll find it as part of a compound like sodium chloride. These low ionization energy values paired with the low electronegativity values, meaning that they don't have a strong attraction for electrons, means that they'll give up their outer shell electron in order to bond. Excuse me. The reactivity, so how easily they'll give up this electron, increases down the group. The reason for that is the increasing atomic radius and increasing screening effect lowers the ionization energy. As we move down the group, we're adding on an energy level each time, meaning that the electron we're going to remove from the outermost energy level is further away from the attractive pull of the nucleus and also has lots more electrons in the inner energy levels, screening the positive charge from the nucleus. The first reaction we'll look at is the alkali metals with oxygen. They form group 1 oxides, and they're so reactive with oxygen that these metals need to be stored under oil. If we look at the sodium one here in the jar, you can see that it looks white. However, we know that sodium is a metal, so it should be shiny. If we were to take one piece of the sodium out of the oil and cut it in half, you would see that the inside of it would be extremely shiny and metallic looking. However, this white stuff would start to form on that surface as well. This is the sodium oxide forming on the surface of the metal, because the metal, as soon as it's out in the air, in the oxygen, it starts to react with it to form this sodium oxide, this group 1 oxide on the surface of the metal, and all of the others react in the same way. The alkali metals react with water to form metal hydroxide, so sodium hydroxide, lithium hydroxide, and hydrogen gas. There's an example of the equation on the screen there for you now. And if we look at the pictures over on the sides, the top one there is the reaction of lithium with water. You can tell it has fizzed up, there's a reaction has occurred. And if this was a video of the reaction, you would see the lithium moving around on top of the surface of the water. It reacts very vigorously, the lithium moves and forms lots of gas. The second one down is sodium. You can see, or you can guess, that this is more reactive as we see a spark, we see a flame being formed. If we were to see this in action, you would see the sodium zipping around really, really quickly on top of the surface of the water, lots of fizzing happening, so it's all happening more vigorously. And in potassium, if we add potassium to water down at the bottom, you can see that we've had a bit of an explosion here. The reason for that is this is an exothermic reaction, a reaction that produces heat. If we produce enough heat, if enough heat is generated, the hydrogen gas will catch on fire, and that's what we see happening here. So we can see as you move down the group, the reaction becomes more vigorous. The reason for this is, like we discussed with that outer shell electron, it's more reactive. The electron is being lost more easily. Finally, just to mention, you should never attempt to react an alkaline metal with an acid. So much hydrogen gas will be released very, very quickly, and you're almost guaranteed that an explosion will occur. We're next going to look at group 7, the trends in the halogens. These are the most electronegative group, so they have the strongest attraction for electrons. What this means is that they can remove electrons very easily from other substances. Just like we said for group 1, these don't exist free in nature. We have to isolate these, the halogens, from their compounds. Fluorine at the top of the group is the most reactive because it has the highest electronegativity value. The reactivity then decreases down the group due to the decreasing electronegativity value. And if we go back to what we mentioned about our trends in electronegativity, the reason they decrease down the group is due to that increasing atomic radius and the screening effect of the inner electrons. A reaction to show this would be displacement reactions. Displacement means removing something from its current position. And so if we react chlorine and bromide ions together, what we're going to see is that the more electronegative atom, chlorine, because it's higher up in the group, will take electrons. It's more reactive, it will have a stronger attraction for those electrons, so it will take electrons to become an ion. The less electronegative atom, the one furthest down the group, will give away electrons to the more strongly attractive one to form a molecule. So your more reactive substance becomes an ion, your less reactive one becomes a molecule. And so the way to explain this using the word displacement is that the more reactive halogen displaces the less reactive halogen from a solution of its ions. So you can see that there is a solution of bromide ions in our reaction here. When we add a more reactive element like chlorine to it, the chlorine will take the electrons to become a chloride ion, forcing the bromide ions to form molecules. The boiling point increases down the group of halogens due to the increasing molecular radius, so the molecules are getting bigger, which gives them a bigger electron cloud, so they can form stronger temporary dipoles. This means that the van der Waals forces holding the molecules together are going to be stronger, and you'll require more energy to separate the molecules out. If we look here just at the boiling point, you can see that at room temperature, fluorine and chlorine have already vaporized. They've already boiled and turned into a gas. So fluorine and chlorine are gases at room temperature. You'll have seen, or you can see in the image here, that bromine in the middle there is a liquid at room temperature, while iodine is a black solid. Some trends in other groups just to mention. Group 2 will react with water in a similar way as group 1, or in a similar trend, I should say. The first ionization energy decreases as you go down the group, so the reactivity with water will increase as you go down the group. Group 8 boiling points, we mentioned these in chapter 5. They will increase down the group for the exact same reasons we just discussed for group 7. Increasing atomic radius, bigger electron cloud, stronger temporary dipoles, and so more energy is required to separate these atoms from each other.